Now in this video lecture we will go through the design equation for flow reactors, right? Before this we derived the design equation for batch reactors, right? And we understood one thing in case of batch reactors, that one of the advantages of batch reactor was that the conversion rate was high in case of batch reactors. And why was that? Because we can leave the reactants for a longer period of time inside the reactor, right? So the more, if we leave it for more time or for a longer period of time, the conversion rate would be high. That is, more reactants will convert into products, right? Because reactants have chance to react, right, for a longer period of time, right? So it's this is how this reactor looks like, right? It does not, in batch reactor we don't have any inflow or outflow. It's just this kind of a tank, right, where we will leave the reactors, right, inside this, where we will leave the reactants inside this tank, right? And if we leave, suppose this is the reactant, right, and if we leave the reactant for a longer period of time, they have more time to react. These reactants have more time to react inside the reactor, so the conversion rate is high, right? So here the conversion rate depends on the time, right? Time for which these reactants are in contact with one another, right? So conversion depends on time, right? More is the time, more is the conversion. So we said that conversion in this case, conversion is the function of time, right? Conversion is the function of time, right? Now since we are dealing with flow reactors, let's see how flow reactors are different from batch reactors. If we have a flow reactor, say like this, flow reactors means there is continuous flow, right, of reactants and products in the reactor, right? Continuously reactants are flowing in, products are flowing out, right? And at the same time of reactants flowing in and products flowing out, the reaction is taking place inside the reactor, right? This is important to understand. At the same time reactants are flowing in and products are flowing out, the reaction is taking place inside the reactor, right? Yeah. Is inflow, right? Suppose from here you have an outflow, right? So inside you have a chemical reaction going on. Inside you have a chemical reaction going on, right? So since here we said conversion is the function of time, so here also we need to find, we need to look similar relation for the conversion. If we want to increase conversion in this case, right, in the flow reactor, what we can do, right? Here what we did, we left the reactants for a longer period of time, so conversion increased. But here we cannot leave the reactants because this is a continuous flow system. From one end reactants are being fed and from the other end these products are being taken out, right? So the only thing we can do here is, if we increase the size of the reactor or the volume of the reactor or the length of the reactor, right? So here time factor can be increased in this way by increasing the volume or size of the reactor. If we have a bigger tank, right? If we have a bigger tank, then it will take more time for the reactants to flow inside the reactor, to completely flow inside the reactor or the tank and leave before leaving the reactor, right? So if I have a small reactor, then these reactants will quickly come inside the reactor, will react and quickly move out. Suppose I have a big this much of length of reactor, then these reactants will take more time, right, to flow out of this reactor, right? That is, they have more time to be in contact with one another. That is, if they are in contact with one another for a longer period of time, then they will react, right, more, and the conversion rate would be high. So here the only way to increase the conversion rate is to increase the size of the reactor, right? By increasing the size of the reactor, we mean we increase the volume of the reactor. So here conversion depends on the volume of the reactor, right? More is the volume, more is the conversion, right? Because more is the volume, more time these reactants are in contact with one another, so conversion would be high, right? So we say that here conversion is the function of volume. Conversion is the function of volume, right? Now, just based on this understanding, let's do one thing. Let's say let FA0 be the flow rate of reactant of, say, any species A, right? This is the molar flow rate. Let's call it molar. This is FA0 is the molar flow rate of any species, right? When the reactants is fed into the system, right? Molar flow rate of species A fed into the system. Here the system is your flow reactor system or the reactor, right? Now we need to find the conversion, right? We are trying to find an expression for conversion first, right? So in order to find the expression for conversion, we need to look here inside the reactor. Inside the reactor, we need to find the conversion rate. We need to find an expression for the conversion based on what is happening or the reactants that we are feeding, like this FA0 that we are feeding into the reactor, how much they are reacting inside the reactor, right? Using that, we'll get to know the conversion. So we know that conversion is, if FA0 is the molar flow rate, that is, molar flow rate means number of moles of FA0 or the number of moles of A that is being fed into the system is FA0, right? So what is the number of moles that is reacting inside the reactor? We know one thing, that if you just recall the definition of conversion that we defined in the first lecture of this chapter, conversion denoted by X is moles of A reacted divided by mole per 1 mole of A that is fed into the reactor. Moles of A reacted per mole of A. Per mole of A, right? This means if I fed 1 mole of A inside this reactor, then how many moles out of this 1 mole, how many moles will react, right? That is your conversion. So this is for 1 mole, right? This is for 1 mole. We have total FA0 mole that we are feeding from here, right? So if this is the expression for 1 mole, right, and this is the total number of mole, right? So total species A that is undergoing chemical reaction or that is getting consumed. When we say it undergoes chemical reaction, it's getting consumed, right? So total species A that is getting consumed inside the reactor would be moles, total number of moles. This is for 1 mole, total moles are this FA0. So FA0 into X conversion, which is this, right? Conversion is for 1 mole, total moles are this. So the quantity of A that is consumed would be FA0 multiplied by X, right? This FA0 dot X. And what is FA0? If we just look, if you want to know it mathematically, this is moles fed. Moles fed divided by time. Right? FA0 is your moles of A fed, right? Moles of A fed divided by time, right? And this would be divided by X, right? X is moles of A reacted, X is your conversion. Conversion means we are talking about reactants being converted into product, right? Total out of the total number of moles that are fed into the reactor, right? I repeat, conversion is, because this is important to understand, conversion is total number of moles converted into products out of the total number of moles that is fed into the reactor, right? So here moles reacted divided by moles fed into the reactor, right? Because if you just want to understand this, it's a simple unitary method where if moles fed, this is moles fed into the reactor. If moles fed is A, right? If A moles, let's say, if A moles fed into the reactor, out of these A moles, say A1 reacted, right? So if 1 mole is fed into the reactor, then A1 upon A moles, right? And this is your conversion for 1 mole, right? So here this is the total number of mole, FA0, right? And this is the conversion per mole, right? Total number of moles into per mole conversion is your total of FA0 that is consumed inside the reactor, which is this. So this would be moles of A reacted divided by time, right? This is the expression. This is your FA0 to X, right? Now we got, this is the one thing that we got, we understood this. Now the second thing is, if you want to find the total out, what is going out is total that you are feeding inside the reactor minus what is consumed, right? That is your equal, that would be equal to the total species going out. I repeat, total species that is going out is equal to, because if what is going out, right, we have to subtract, because what we are flowing in, right, is getting consumed inside the reactor before it leaves the reactor, right? So we have to subtract this, right, from this in order to get this. So it's moles flow rate at which A is fed to the system, moles flow rate at which A is fed into the system minus moles that undergo chemical reaction, or moles rate at which A is consumed, right? Moles rate at which A gets consumed is equal to moles rate at which A leaves the system. Right? This is moles rate at which A leaves the system. Right? This is your FA0, right? Which is fed into the system is FA0, right? Minus what is consumed, right? What is consumed is this FA0x. FA0x is equal to what is going out is your FA. FA. This is your FA0x and this is your FA. Right? You can clearly see these quantities right here. So it would be F is equals to FA0. You take FA0 common, 1 minus x. This is your design equation. Right? This is an expression that contains your conversion x. Right? This is your design equation for flow reactors. Design equation for flow reactors. Now we would be using this equation for all the flow reactors, Cstr, PFR and PBR, right? For all the flow reactors to modify the mole balance equation in order to get the design equation. Once you have the design equation, you can size the reactor. That is, you can find the volume of the reactor required for the X conversion, required for the conversion which is given by X. Right? We'll just understand this. We have done this in one of the previous lectures also. I'll just brief you on this. Right? In order to write the design equation for any reactor, what we do is we modify the mole balance, right, using conversion, or we write mole balance equation for that reactor in terms of conversion. Right? So what you get, right, is your design equation, and once you have the design equation, you can find the volume of the reactor, right? Or what we say is, once you have the design equation, you can size the reactor. By saying size the reactor, we mean we can find the volume of the reactor required for the specified amount of reactants to get converted into products, right? So I'll just write down the steps. You have mole balance equation, right? You modify it or write it in terms of conversion X. Right? Once you modify it in terms of conversion X, you have the design equation. Once you have the design equation, you can size the reactor. By sizing the reactor, we mean we can find the volume of reactor. Sizing the reactor means finding the volume of the reactor. Once you have the volume of the reactor, right, then you can, once you have, what we are basically doing is we are deriving a relationship between conversion and the volume of the reactor, right? So that you can find the volume of the reactor, right, required for specified amount of conversion of reactants into products. We'll just take one example of Cstr, then it will be more clear, right? So we'll write down the mole balance equation for first we'll write down the mole balance equation for Cstr. Let me just rub this off. Right, for Cstr, this is continuous turret tank reactor. One important thing about continuous turret tank reactor is that the concentration of the reactants inside the reactor is same in every direction, because the stirring is so efficient that the composition or the concentration of the reactants will remain same everywhere inside the reactor, right? So in continuous turret, if this is the continuous turret, whatever is the concentration inside the reactor, the same concentration would be leaving the reactor. This is what it means, right? I'll repeat. since since the stirring is very efficient, so the concentration is same, right? Here also, here also, here also, here also. At every point, the concentration of the reactant mixture is same, right? So whatever is the concentration inside the reactor, the same concentration would be leaving the reactor, right? Now let's just write down the mole balance equation for the Cstr, because that is what we need to change it into. That is what we need to modify using conversion, right? So we know from the mole balance equation we derived earlier that mole balance equation is Fa0 minus Fa upon, this is mole balance, V is equals to Fa0 minus A upon R. This is your mole balance equation. Right, this is your mole balance equation for Cstr, right? This is mole balance equation for Cstr. Now we will write, in order to find the design equation for Cstr, we would be modifying this equation, or we will write this equation in terms of conversion, right? This is what is the second step. So as we derived the design equation, this is the design equation for all the flow reactors. Using this relation, we will write these equations, mole balance equation, in terms of conversion, right? So here this is your Fa, right? This is your Fa. What was going out was Fa. I missed this A here. Sorry. So V would be Fa0. I'll just substitute the value of Fa from this equation, right? It would be Fa0, right, minus Fa0x, right? This would be Fa minus Fa0x, right? Right. So this is, so we just, it's simple, we just substituted the value of Fa from the design equation, right? And what we got is Fa0 minus Fa0, right? And this is minus, right? So here it is minus, this will become plus. This is minus Ra, this will become plus, right? Since this is minus here, so we have minus here, so this minus minus will become plus, right? These two will cancel out, right? So here we have now volume is equals to Fa0, right? What is fed in the reactor, dot conversion x, right, divided by reaction rate, right? So this is your design equation. Using this equation, if you see, we have a relationship between volume of the reactor and conversion x, right? Using this relation, you can size the reactor. By saying size the reactor, when you have this x, when you know the value of x, that is how much of reactant you want to change it into product, right? What is the, when you have the requirement that this specified amount of reactants needs to be converted into products, right, which is your conversion x. So using that, you can find the volume of the reactant, right? So this is your design equation for Cstr, right? And just as I said earlier, the reactor is perfectly mixed because of efficient stirring, right? This reactor, this is perfectly mixed, right, because of efficient stirring. So what is going out, right, the exit solution would have the same concentration as inside, right, because of perfectly mixed. right? I hope this is clear. This is for Cstr, right? So in the next video lecture, we will look the same equations for PFR and packed bed reactor, right? So I hope this is clear to you. Thanks.